In this video, let's learn about symbolic constants, 64-bit programming, and data transfer instructions. So first, let's talk about symbolic constants, which is not a new concept for most of you. With Java and C++ and C both, they all have this concept of defining or assigning a constant to a identifier. And when you use that identifier, you're actually using the constant that identifier represents. So there are multiple ways of defining symbolic constants in assembly language. And we're going to talk about those, and then we are going to talk about how to calculate the size of an array and size of strings. Okay, so just like in C++, and you could use a equal sign to give a identifier or a name equal to an expression, and use that name to represent that the integer, right? The expression evaluates to. It could be a expression or just a integer, right? It could it could be a 32-bit integer or expression that evaluates to a 32-bit integer. The equal sign directive constant can be redefined. Throughout your code, you could start out, let's say a count is defined as 500, and later on you can define it as 100. So it could be redefined. The name is called a symbolic constant. So if in your code that you are using a certain number, let's say you're writing an application for scheduling classes, and there is a limit on class size, let's say 35. Okay, and then you can define class size is 35, right? And then throughout your program, you can just refer to the name class size instead of use 35. The benefit of that is that, so if later on there's a policy change, let's say the school gets more funding from the states, we're going to reduce the class size. Now the class size is no longer 35. Let's say it's 28. So all you need to do is change one line of code, right? You don't have to change the rest of your program. So that's it is generally considered a good programming style to use symbols, right? If possible. In here, you define count as 500, and if somewhere, and you have this move instruction to register AX from count, which is considered an immediate value, and you basically is moving 500 into the register AX. The second way of defining constant symbol is using the EQU or equal directive. EQU can be used to define a symbol as either an integer or a text expression. It cannot be redefined. And there are three formats of it. It could be this name is equal to expression, right? This is kind of like the equal sign that we saw earlier. Or it could be a name equals to a symbol, right? And then after that, every time you refer to the name, you're referring to a symbol. And it could be a name equals to some text that's in quote. It's bracketed by this ankle braces. Okay, let's look at a few examples. So if you say pi equal ankle bracket 3.1416. So in this line here, 3.1416 is being represented like characters. You don't interpret the numeric meaning of it. So, but however, when you use pi later, right, and the pi will be substituted with 3.1416, at that point, it will be a number. Or you can define press key is equal to this particular string, right, terminated by a null character. Okay. If you do that, and in your data segment, and you define a label prompt, which is using a directive type, and when you use press key, this press key basically will be this particular string, followed by the null character without the ankle braces. Let's look at another example. So in here, we define matrix 1 equals to 10 multiplied by 10. So this will be, this is an expression, right? This will be interpreted. This will be evaluated to 100. So matrix 1 is being defined as 100. However, matrix 2 is not equal to 100. It's actually equals to 10 multiplied by 10, because the contents inside the ankle bracket being interpreted as texts, but it will be used later. It will be evaluated later in context. Okay, so after you've done that in the data segment, and if you define M1 label, right, M1 with a directed word followed by matrix 1, this line is the same as M1 word 100, right? The M1 is being initialized as 100. And then when you say M2 word, matrix 2, that will be the same as M2 word being initialized as 10 multiplied by 10. And this will be, at this point, evaluated. Once you use M2, and you'll see the word, defined by label M2 has an initial value of 100 also. It's just that, at the substitution time, okay, things in the ankle braces are not evaluated or interpreted. It will be copied, as text, as they are. But in this context, right, the 10 multiplied by 10 has its own meanings. So it will be evaluated. Text equal directive is very much similar to equal, but it can be redefined. So equal cannot be redefined, but text equal can be redefined. And text equal, despite the name, can define a name to a integer. The integer will be the result that starts with this percent sign and followed by an expression. This expression will be, the whole thing will be evaluated to an integer. Let's look at some examples. So the first one, continue message, is defined as text equal. Do you wish to continue? Yes or no in ankle braces. And then you also define roadside is equal to 5. So this is with just a regular using the equal sign constant, right? And then in the data segment here, when you define prompt 1 as a directive of byte followed by this particular symbol, right, or label, and this will be substituted by the string in quotes. Okay, and then if you say, okay, I'm going to define count using text equal to percentage sign followed by an expression, you are going to evaluate this particular expression. So now count will be the same as 2 multiplied by 5 is 10. So count is being defined as 10, as an integer, 10. So lastly, when you define, this is actually called text macro because you are defining the setup AL as this whole instruction here, right? And you say text equal to move AL count. Now count is 10. So you're going to move this whole instruction in ankle braces is defined as a macro represented by setup AL. So every time after this, from this point forward, when you use the symbol setup AL, you are actually using this macro. Okay, so how do we calculate the size of a byte array? So we use a current location counter, which is represented by a $sign. So the following declare a variable name self pointer and initialize it with the variable's offset value. Okay, so self pointer is a double word because we are using a, let's say, assume we are using a 32-bit system, right? The address, memory address, is a double word, 32-bit. And if you initialize it as a $sign, this $sign actually represents the address of this line, this particular label here. So self pointer, it basically contains the address pointing to itself. Okay. Now we can use the $sign to calculate the size of a byte array. We basically let's look at the example here. We're going to define a byte array with 4 elements, 10, 20, 30, and 40, right? Called list. So 10, 20, 30, and 40. Not sure why. I think this is an error here. This H is an error here. Unless we need to put in all H's. Hang on. I think the example would be correct when we use this. H. 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 Okay. So it has, each byte, right, contains a hexadecimal number, right? 10, 20, 30, and 40. What is the size of this array in terms of bytes, right? Because we are, in x86 system, the address is, by bytes. At which byte, what address, at which byte. So what you need to do is the $, which is a cell pointer here. Okay. And when you use the $, here, right after, because memory is being arranged in consecutive manner, right? The first byte is 10, second byte is 20, and so on and so forth. And then the next byte, address of the next byte is the $, right? So in this line here, when you reference $, in this line here, it's referencing the address right here. So if you use the $ minus the address, you subtract the address at the beginning of the array, and you get the size. Okay. Okay, so what if I define, instead of a byte array, I'm defining an array of word. So here's the array of 4 words, right? With the 1,000 hexadecimal, 2,000, 3,000, and 4,000, right? Each one of these take up a word. So the size, if you calculate the list size right after this line, it has to be right after this line, is the, the current address of this line minus the address of this array, the beginning address of this array. Because each word has 2 bytes, so you divide that by 2. For double word, you're going to divide that by 4. So that's how you calculate array sizes in terms of bytes. Okay. All right. So next, let's talk about 64-bit programming. So when you went through Kip Irvine's web site, on the instructions how to set up, 32-bit and 64-bit environment, and I asked you to take a look at the difference between 32-bit and 64-bit programming. So there are some differences. So in the 64-bit program, the following directives are not permitted. Invoke is not permitted. ADDR is not permitted, and we'll talk about ADDR later. Dot model, dot 386, dot stack, right? These are not needed. And there are other non-permitted directives as well, and we'll cover those in later chapters. Okay, so this is a sample program of adding 2 numbers, 64-bit. as you can see, now we will define the exit process prototype here, except that there is no parameter, right? There's no double word parameter defined for the exit process. There's still data segment and code segment. In here, the data segment, we define sum as double word, and then we initialize that to 0. Okay, so the main program, by and large, is the same, and you can use 32-bit registers and 64-bit registers, and here we're just using 32-bit registers. Now, instead of invoke exit process and pass in the exit code, we are going to move the exit code to the ECX register. And then we're going to call, instead of invoke, we use call to call the exit process to end the program. So there's no .386, .stack, etc. And also there's no dot model. And one thing to note is that the call instruction cannot receive arguments, as you can see here. Right? It just called this procedure, and it did not provide an argument. And the argument is implicitly being stored in the register ECX. And you can use 64-bit registers, of course. Okay, so that's a summary of what we covered. Let's see, operand types. Okay, let's continue on. At least we'll cover from operand type all the way to move instructions. So operand types, there are, when we are using, instruction mnemonics, right, such as move, add, SUB for subtract, we use operands, right? There are 3 types of operands. The first one is immediate. Immediate basically is a constant integer. Right? It could be an expression, but it gets evaluated to an integer. And the whole value is encoded within the instruction itself. You just write it out. Another operand type is registered. Right? You use a name, the name of a register. And the register name is actually converted to a number and then encoded within the instruction, right, in the machine code format. And which is the same as the constant, which is the immediate value. You have seen that in our listing in a couple videos ago when we talk about listing file, right? And you can see the name of a register gets encoded in the instruction, right? Same as the value, the immediate value. And then the third type of operand is memory, right? Such as the sum here. It refers to a memory location. So it could be memory. And the memory address is encoded within the instruction, or a register holds the address of a memory location. We haven't seen the second scenario yet, but just keep in mind. There are three types of operands. Immediate, which is immediate value, or a registered, or a memory location. So you will see, in your textbook, there are references for move, for the MOV, and here it will list the opcode. Okay, different move, involved with different registered or memory location. It use different machine opcode. And then the mnemonic is like this, right? When you see the M16, M of 8, and what do these symbols mean? So I have a table here on this slide, and it's going to explain all this, shorthands with meanings of them. For example, Reg 32 means 32-bit general purpose register. It means it could be EAX, EBX, ECX, so on. And register 16 means just a bunch of 16 registers. IMM8 immediate value means it's an 8-bit immediate byte value. Okay. And then there's a memory location. So in here it says, register or M32 means that a 32-bit operand, which can be a 32-bit general register or memory double word 32-bit. Okay, direct memory operands. So a direct memory operand is just a name reference to storage in memory. So the label, when you use a label in the operand of move, the memory reference is automatically dereferenced by the assembler. Now, when you learn pointers in C and C++, you probably have seen the word dereference. Dereference means that you are going to retrieve the value being referred to by a reference, by address. Okay, so for example, here you define a variable var8, which is using a directed byte, which is you define the size of a byte, and the initial value is 10 hexadecimal. Now, when you say move var1 to register AL, which is the lower byte, the lowest byte of a EAX register. Instead of this var1, you are not actually moving the address, whatever that is, to AL. You're moving the value stored in this address. That's what the reference means. So you're really moving the number 10 hexadecimal to AL. So now after this is done, this is 10H. Now there is a dereferencing alternative syntax. That is to put the square bracket around a variable, the memory location variable. That has the same meaning. So that for those of you who learn C or C++, this comes across as a little bit weird because you're saying the, usually with C++, the referencing, you put an asterisk, right, in front of the variable, the pointer variable. And when you use the pointer itself, you just use the variable. But in this case, either one will get dereferenced. Okay. So the move instruction, it moves from source to destination. And there are a few rules governing move. You cannot move an immediate value to a segment registered. Both operands of move must be the same size. Okay. And both operands cannot be memory operands. So it could be one of them is memory, the other one is register, or one of them is a memory, or the destination is memory, but the source has to be an immediate value, right? It cannot be, both operands cannot be memory operands. And the instruction pointer registered, right, such as IP, which is a 16-bit instruction pointer, EIP, which is 32-bit instruction pointer, or RIP, which is 64-bit instruction pointer, cannot be a destination operand because the values, right, when you execute one instruction, you advance to the next instruction. That is done by the CPU, by the system. And so you are not, the user programs are not allowed to change them. They are changed by the system. Okay, so those are the rules for move. Let's look at a few examples. So in the data segment here, we are going to define a label count as byte with the initial value set to 100. And then we have a W val, which is a word with the initial value set to 2. Now, in our code segment here, we are going to move count to BL. Now, remember, count is a byte, right? BL is also is an 8-bit register. So this is fine. You can move the count to BL. And you can move a W value, a word, which is 16-bit to AX. And AX is a 16-bit register. Okay. And you can move AL register to count because count is a byte. AL is 8-bit, right? So that also works. So if you look at here, AL is the lower byte of AX. Right? AX is 2 bytes, 16-bit. So when you move 2 to AX, the low AX has 2 bytes. Let me draw a picture. Hello. I can always cannot pull up my whiteboard here. Okay. So you're gonna see some pictures here, I think, later. Okay. So AX is the 16-bit portion of the EAX register, right? So when you move number 2 into AX, the upper byte is all filled with zeros, right? And the lower byte is 2. So the AL has this lower byte number of AX. So that's why here, when you move W val, which is initialized to 2 to AX, and then you're going to move AL to count. Now count has a new value, right? The value of count gets changed from 100 to 2. Now remember, these two things has to be the same size. Count is a byte, AL is a byte. Now the following three they are not permitted, right? To move a word to a byte to a 8-bit register is not allowed. Okay, and to move a byte to a AX, which is 16-bit, right? You move 8-bit to a 16-bit is not allowed. And also, EAX is 32-bit, right? A count is only 8-bit, a byte, so that's also not allowed. So the big picture takeaway is that the standard move instruction format is you can move from registry to registry, registry to memory, from memory to registry, from a immediate value to memory, or immediate value to registry, right? All these things, these operands, these two operands, they all have to be the same size in the same move instruction. And you cannot have two memory as operands. Okay, so explain why each of the following move statements are invalid. DS. So DS is a segment register, right? You haven't learned details on segment register yet, but you are not allowed to move immediate value to segment registry. And here, WVal is a word, okay, and it cannot be moved to a ESI because ESI is a 32-bit registry, a 32-bit register. And then EIP is the 32-bit program's instruction pointer. It cannot be changed by the user. Okay, and then the next one, the destination cannot be an immediate value. And then lastly, you cannot have both operands as memory labels. Okay. So overlapping values. We are going to discuss this in the next video.